Hello everyone, my name is Dan Purkat. I am the Graco Process Division Global Product Manager, specifically for the industrial product line. Today, we're going to talk about QUANTM, Graco's next generation electric diaphragm pump. We're going to run through some basic operation, features and benefits that will give you a better idea of what the pump is, how it works, and answer any questions that you may have. We're standing today in front of a QUANTM i30 1-inch pump. This is the North American version, so this is a 120 volt AC single phase pump. So what we're going to do first is we're going to look at some of the components on the pump, what they are, and we'll get into how they work and how they operate in just a moment. So if you look at the pump, obviously on the face, we see the control cover. We've got our one-touch control knob. This is going to control pressure and speed at the same time. Much like the air regulator on your pneumatic pump that you're familiar with today, you're simply going to turn the knob up to increase the speed, and the software is going to interpret what's going on in the system to vary that pressure to where it's required. We've got an LED light here, multicolored. It is red, green, and amber. What that is going to do is that's going to give you indications as to the pump's status and potentially if there is something going on downstream where the pump has stopped, something has gone, there's some sort of error. The pump does have onboard diagnostics. A series of colors and flashes will indicate what is going on with the pump. We've got our I/O port right here. So this is our input and output. We've got 3 functions on this, 2 inputs and 1 output. We can take any open-close digital signal. So think of your float switches, a flow meter that has a set point on it, any open-close dry contact. We can also take a 4 to 20 milliamp signal to vary the speed in the place of the local control knob. And we have 1 output back to PLC. We can tell your PLC whether or not the pump is running or not. So in the event of some sort of failure, possibly a blockage downstream, we can report to PLC that the pump has stopped pumping. At that point, if you get an error to your PLC that the pump has stopped, an operator will have to come back and interpret what's going on with the multicolored LED. The pump does not currently have the functionality to tell you why it stopped, only that it stopped. Okay, so then what we'll do is we'll come back as an operator, we will interpret what's going on with the LED based on color and flashes to make the correction to the pump or the system to get everything back up and running again. Other than that, if you look at this pump, it is completely the same as any Graco pneumatic Husky pump. Modular fluid components, in this case, this is an aluminum pump. You can see all of these components are the same. The only thing that has changed here is the drive. As I mentioned earlier, this is a North American 120 volt single phase pump, so all it needs to do is be plugged into the wall. And we're off and running at that point. The first thing we're going to do is plug in the pump. And what you'll notice is our multicolored LED goes to red. When we start the pump is going to go through a homing sequence. The light is going to turn amber as the pump orients itself and calibrates itself. You'll see we have an amber light. The pump is going to cycle slowly as we go through the homing process, and it's going to turn to green. At this point, the pump is pumping as normal to its set speed on the single touch control knob. At this point, what we'll do is we'll put the pump into normal operation. As you can see here, we have a red LED. When the red LED is indicated solid, that means that we have power present in the system. This is a very important warning to operators that this is energized. The pump is plugged into power or hardwired if that were the case, and we have power present. So that an operator should know not to pull this cover off because this is energized. At this point, what we'll do is we'll put the pump into normal operation by simply using the single touch control. You'll hear the pump begin to cycle, and the LED will move to green. Solid green indicates normal operation. The pump is chugging away, we're siphoning material and discharging it off of the outlet manifold. The pump will continue to do this basically indefinitely. An operator can come vary the speed. You will hear the cycle rate pick up. Very, very simple. As everyone should know at this point, when we designed this pump, the point was to make this pump act and operate just like a pneumatic pump. One of the main benefits of a pneumatic diaphragm pump is that it can stall against pressure. We can turn a valve to shut the flow off, or in the event of a blockage downstream, it will not damage the pump. I'm going to demonstrate that now. As I close this valve, the pump is going to go into a stalled condition. What you will notice is that the pump is flashing green. We went from a solid green to a flashing green LED. The green LED in the flashing state indicates that the pump has stalled against pressure. We can also see that indicated here. We're at about 30 psi back pressure based upon where I have the knob right now. We view this as a normal operating condition, so the light stays green. Even though it's flashing, green is a normal operating condition. In this example, a stall. I'm going to open this back up, and what you're going to notice, because the pump is in a standby mode right now, it is looking for the valve to open. And what that's going to do for us, which is very unique to the Graco QUANTM pump, is that the pump will immediately stop pumping, or start pumping rather. You will not see any delay once I crack this valve. You heard it start to roll, and it's opened right back up again. Indicator LED went to green, solid green, which means normal operating in a steady pumping state. Okay, what we're going to do now is we're going to demonstrate a feature that's very unique to the Graco QUANTM pump, and that is an auto prime feature. For those who are familiar with diaphragm pumps, you understand that when the pump is cycling quickly, they don't like to pull prime as well. The reason for that is because the ball and the seat need to spend a certain amount of time connected in order to pull suction. So if that ball, and the ball is sitting on the seat for a good length of time, it pulls great suction. If the ball is essentially dancing on the seat very quickly, they don't like to pull suction. QUANTM suffers from the same problem when it's pumping at high speed. So what we've done is we've built into the system the capability of the pump to understand when there is fluid present in the fluid chamber. If it does not see that fluid, it automatically will slow the pump down, give those balls and seats more time together to pull suction. We're going to simulate that now. You'll hear the pump is cycling as normal. The pump is dry. I've got the valve closed right here so it cannot pull suction. You will now hear that the pump has slowed down considerably. What it's doing is it's slowing the cycle rate and changing the cycle length a little bit, give the ball and seat more time together. As I open this valve, the pump is going to begin to pull prime. And there you hear it took right off. It cycled slowly. The pump cycled slowly, it got prime, and it sped up to my set point on the one-touch control. That is how auto prime works. It is looking for fluid present in the system, and it can tell that by the amount of amperage that it's drawing. The software interprets that and it moves us in and out of auto prime as required. Okay, now what we're going to do is we're going to simulate some very common input and output signals that a customer would want to use with the pump. In this case, what I've got is I've got a level sensor simulator. We're going to plug into the I/O port and we're going to use the level sensor to turn the pump on and off as if you had a tank that you were trying to fill, and when it got to a certain level it would shut the pump off. This is a simple, on our ordinary location pumps, this is a simple M12 connector. It's worth noting on the hazardous location pumps, this will be hardwired. The pump is going to come with a plug here. They will pull the plug out and install the input and output cables as required. What you'll see, I can turn the pump on and it functions as normal, okay? Because all we've done with this level switch is given us the ability to control the on and the off functionality, not the speed. The speed is still controlled locally, but now we have an on-off signal to the pump in the form of this level sensor. So right now we are simulating a tank, for example, that is filling, and now I'm going to show you what happens when we get the tank to the level we want. The pump stops. I've simply manually pushed the float into the upward position. We've now stopped the pump. The tank draws down, the level sensor trips, and we're off and running again until we bring that level up enough to trip the float. We can do this all day. On, off, on, off. Very, very simple. We're just providing an open-closed switch to the pump for that functionality. What that does for us also is it disables the local control for the on-off functionality. For example, the pump is running right now, it shuts off. An operator cannot come, I'm turning the knob throughout its range, an operator cannot come and turn the pump back on. Because what we've done is we have grounded the on-off functionality of the knob through the I/O port. So it will only turn on with the float switch. There you go, you can see what we're doing here. There is one caveat to that. We are now in the operating condition, as you can hear. Because this is an electrical device, in order to get the approvals that we require, we have to give an operator local off control in the event of an emergency. I can shut the pump off, okay? That's one thing that's important to remember. This is not an e-stop, it is local off control. They can shut the pump down. Let's say something happened on the outlet side, there was a blockage, something happened, maybe there was a leak, to give the operator the control to shut this off, okay? We have to do that in order to get the certifications we require. We can then start resuming normal operation because we're waiting for the tank to fill, and we can go back, fills up, it stops again. Okay, now as the second part of the input and output functionality of this pump, we're going to simulate a PLC controlling not just the start-stop function, but the speed and pressure control remotely. So we have a little signal generator here that we put together, and if you notice right now, I've got the knob at about the 25% mark. Our light is red because we have power present, the pump is not pumping. What I'm going to do is I'm going to simulate the on-off signal to the pump and use the signal generator to give us some speed. You hear the pump is pumping away. I can now vary that speed remotely anywhere through the pump's range. You hear we're speeding up. I can turn this down to any speed I want. Also, I can shut the pump off. I can turn the pump back on. This is simulating two very common signals from your PLC. A simple open-close switch and a 4 to 20 milliamp signal to control speed and pressure. Very easy, very simple. One thing that we need to note is, as we talked about with the float switch, our goal here is to eliminate as much local control as possible. Example being, we've got a control room that is operating the pump remotely at a set point. We do not want operators to be able to come back to the pump and vary that set point, which may contaminate the process. So if you look, I can turn the knob and I cannot vary the speed. The only way I can control the speed of this pump is remotely with the PLC. The one caveat to that is the same caveat we had with the float switch. In the event of some sort of leak, some sort of emergency, an operator can come and turn the pump off. Again, not an e-stop, but local stop control, which is required of an electrical device. Okay? If they come back and turn the knob on, it will automatically go back to the set point from the PLC. Again, it cannot be varied. I can turn this knob in any direction I want. It will not vary the speed. The only way to do that is from here. A second thing of note is, in the event an operator or someone comes by and disconnects this I/O cable, the pump is going to shut off. Because much like the float switch, when we hooked up to this, we grounded the control knob. So it's non-functional now. You can turn this all you want. We can bring it to the off position. We can bring it back to the max position. The pump will not function. That's a safety feature that if someone disconnects this, or if it gets cut, that the pump will cease to operate. The only way to override this is to do a complete power cycle. And that means to disconnect power. Either unplug the pump, or if the pump is hardwired, someone has to turn the breaker off to the pump. At that point, it will reset the software, and we are going to go back to local control until someone plugs another piece of hardware in to the M12 connector. We're going to wait for the capacitors to discharge. You'll see the light is still red here. Even though I unplugged this, there is a bank of 6 very large capacitors, which means it's still energized inside the control. It's going to take about 20 seconds for this light to go out, which it just did, to indicate that there is no power left in the system. We'll go ahead and plug this back in. We're going to go through our homing cycle again because we cut power. The light was amber for about 3 seconds, and now we're under normal operating conditions with local control. The only way we change that again is plugging in the I/O cable. We'll show this again quickly. And now you see I have no local control again. It's all going to be from here. It's all from the PLC. And now what we've done is we've taken control again from the local, and it's all remote. So again, we can't do anything here. All right, now we want to focus on and demonstrate a feature we call auto restart. If you know anything about electrical devices, pumps in particular, when there is a power failure, just because the power comes back on does not mean the pumps are going to come back online. I'll use an example. You've got an electric centrifugal pump that's hooked up using a VFD. If the power goes out, comes back on an hour later, someone has to go power cycle that VFD in order to turn the pump back on. Electrical devices are not in order. With some certifications, electrical devices cannot automatically turn back on. We have built into this a warning system that will allow our pump to come back on in the event of a power failure without power cycling the pump. Okay, we're going to demonstrate that now. We're going to put the pump into normal operation. We know the operation is normal. How? Because the green light is solid. We are now going to simulate a power failure by simply unplugging the pump. Okay, so we've got some sort of blackout or brownout condition at the plant level that has shut the power off to the plant, and the pump is no longer functioning. You'll see the red light is still present because we're discharging those capacitors still, so this is going to take a few seconds. And what we're going to be doing is when we go to plug the pump back in, which is going to simulate the power coming back to the facility, you're going to notice a couple of things. First, you're going to hear an audible klaxon type sound. It's going to sound for about 1.5 seconds. Then we're going to see the light go to amber. Because we lost power, the pump has to rehome, it has to recalibrate. Because when it lost power, it doesn't know where the ball screw, the diaphragm shaft in this case, stopped. So we need to locate that again. So if you look, we still have the control knob in an on position because we lost power while the pump was pumping. I'm now going to plug the pump back in, which will simulate that the power has come back on. You heard that audible noise that the pump made. The light was also amber throughout that process. As the pump was rehoming, it was recalibrating where the diaphragm shaft was in relation to the sensors in the control. By giving that audible warning, we alert any operator in the area that the pump is about to come back online. That is how we are able to utilize electric pump technology and still have the pump restart just like a pneumatic diaphragm pump will. Because we know that pneumatic pumps will come back online automatically once the compressor is reset. So again, we talk about this with QUANTM quite a lot. We need this to function just like a pneumatic pump, and part of that is being able to restart when the power comes back on.